The objectives of Chapter 6 is first to introduce the concept of entropy through the deviation of the inequality of classes. That will be the main topic for this part of the lecture. In the next lecture, we're going to talk about Gibbs property relations which involve entropy. Essentially, we're going to combine the first law with second law and use them to predict the entropy change of solid, liquid, and the gases when their state changes. We are going to highlight a group of process called polytropic process and estimate how the introduction of entropy affect the polytropic process analysis. And in the third part of the chapter, we're going to discuss entropy generation and the entropy balance equation for closed systems. I urge you to think this way. If chapter 3 is designed for energy balance for a closed system, this chapter deals with entropy balance for closed system. Next chapter deals with entropy balance for open systems. So I also urge you to think there's a parallel development here because chapter 4 deals with energy balance for open systems. So chapter 7, the next chapter, will deal with how the entropy balance can be applied to open systems. Then finally, we're going to zero in, focus on the entropy equation applied to heat engine and the heat pumps. Now let's talk about the inequality of classes. These equations are derived from the analysis of cyclic process, which leads to the definition of entropy. There are 4 blocks of equation on this slide. The first 2, we focus on heat engines. In the last 2, we focus on the refrigeration cycles. And the first group of equations is designed for the analysis of reversible heat engine. The second block deals with irreversible actual heat engines. Okay, let's look at the first equation for reversible heat engine. As we recall, if when we analyze a heat engine that involves 4 consecutive processes, 2 of them are adiabatic, 2 of them are isosomal. Therefore, when the working fluid finishes a complete cycle, integration of Q, integration of heat transfer, resulting in 2 terms. One is the heat transfer to the working fluid at the high temperature minus the heat rejected to the low temperature reservoir. We know this is going to be greater than 0 because the difference is the work performed by the heat engine. Next, if we look at the second equation, this equation essentially means we integrate dq over t for a complete cyclic process. Again, we have two adiabatic processes in the entire cyclic process, which do not contribute to heat transfer. Only two isosomal processes contribute to heat transfer. So we can write this integral into these two terms. From the discussion of last chapter, we know that Q ratios equals to the temperature ratios. Therefore, this term, this difference is 0. Then let's look at the irreversible actual heat engine. Integration of this dq will still be greater than 0. However, as we recall, for an irreversible heat engine, because it's irreversible, the heat being rejected to the low temperature reservoir is going to be higher than the Q sub L for idealized heat engine. Therefore, we can apply this relation later on to this integral of dq over t results in this equation, which is not going to be 0 like this. It's going to be smaller than 0, mainly because Q sub L for actual process is going to be greater than QL in the ideal situation. Therefore, this portion of the equation is called Clausius inequality. If we rewrite this integral smaller than 0 and place right here, and put what we derived here, combine them, we get this portion of the equation. Now, this equation tells us two things. Number one, in the actual process, when the fluid complete a complete cycle, the overall heat transfer, integral of the heat transfer over T is going to be greater than the idealized cycle. Number two, when the fluid complete a complete cycle, we have ds, we have this equation, integral of dq over t always equal to 0. So it seems when the fluid return to the original position, there something doesn't change. A property associated with the fluid doesn't change at all when it returns to the original state. And this property seems to be related to dq over t. And this is how entropy will be defined shortly. I just want to put this portion right here to alert you. This is something which will come up. And the analysis of a refrigeration cycle is similar to what we did before for the heat engine. Integral of dq when the fluid made a complete cycle in the refrigeration cycle, QL minus QH is going to be smaller than 0 because QH include the work done on the fluid. Similarly, similar to the heat engine, integral of dq over T yield two terms because two adiabatic term doesn't contribute to heat transfer. Only the two isotomal process contribute to these two terms. Again, from last chapter, the ratio of QL to QH equal to TL over TH. Therefore, these two ratios yield a zero difference. They are essentially identical quantities. If we look at the irreversible refrigeration cycle, integral of dq again is smaller than 0, but we understand for in irreversible refrigeration cycle, the Q term for an actual irreversible refrigeration cycle is going to be higher than idealized heat transfer. Therefore, we have, when we apply to the integral of dq over t, this Q term is going to be greater than this Q, which results in this equation, which is identical if we look at this portion of the equation, which is identical to what we placed here for the heat engine. Okay, once we understand the deviation of the inequality of clauses, we put in here this integral of dq over t in a cyclic process yield a number smaller than 0, small or equal to 0. And when it equals 0, it means the process is reversible. At the bottom of this slide, we use example we discussed in the last chapter for this verification. If the two reservoirs for a heat engine are at 550 degrees C and 300 K with work being performed by the heat engine is 450 kilowatts. We are given the heat transfer, we want to prove it satisfies this inequality, which essentially use the equation we derive only 2 terms left, and we can easily prove that this term is indeed smaller than 0. Now, we're going to prove that entropy, we're going to introduce the definition of entropy now. It's a very important property for the rest of the semester. First, before we formally introduce the definition of entropy, we look at this quantity, dq over t is a function independent from the past. When we make a change from state 1 to state 2, this property is independent of the past. Okay, in order to prove this, we take this integral through two different passes. One is A and B. The other cyclic process is from 1 through C to 2, then return from the same segment. So these two integrals are represented in these two lines. The first segment and the second segment. For these two cyclic integrals, the second pass is the same, so they are identical. We can eliminate when we compare them. Then the analysis of these two reversible paths is these two processes from state 1 to state 2 through path A, and from state 1 to state 2 through path C, dq over t are the same. They are identical quantity, so it doesn't depend on the path. So this dq over t is a state function. This is the major conclusion. Now, the deviation is based on the assumption all these three passes are reversible. However, since entropy is a state function, the change doesn't depend on the path. So we can say any state on this map will have a specific entropy associated with it. And then the change of entropy from state 1 to state 2 can be represented by this integral. And here I also need to mention the difference between capital S and the lowercase s. Capital S denotes the total entropy change. Low ds represents the specific entropy change. That means it's based on per unit mass basis. It's like internal energy and the enthalpy. We also have total internal energy, specific internal energies, since in that nature. Okay. With the understanding that all fluids have a property called entropy at a specific temperature and pressure, we can represent this new property on a diagram called TS diagram. It represents the fluid entropy change as a function of temperature. And on this diagram, we have several lines, and I would like to introduce you one at a time. When the fluid changes the state, temperature remains the same, but the entropy will increase. So evaporation can be represented by a horizontal line. At different temperature, we have different horizontal line. Therefore, we can construct a phase envelope like this. On the right of the phase envelope, it represents saturated vapor. All the points on the left represent the saturated liquid properties. Then we also can construct isobaric lines because fluid evaporation also happen at the same saturation pressure. So we're going to have a horizontal line represent the pressure, but when we heat up the gas even more, the gas enters the superheated region. On the right represent superheated region, and we know the pressure will go up like this. And for constant volume line, constant specific line, we have something like this. The slope is higher inside the phase envelope and outside the phase envelope. And we can also construct constant enthalpy line like this. We can also construct 10% quality line like this, or 80% quality line like this, or 50% quality line like this. This is TS diagram. TS diagram will be very, very useful in our subsequent analysis. If we are given a TS diagram, bear in mind that the entropy of the mixture can also be calculated based on the entropy of the liquid at the one end and the entropy of the vapor on the right. Combine these two quantities just like we did for enthalpy and the internal energy. Then, we have introduced you all these lines. Then we can move into the next slide. This is a enthalpy entropy diagram. It's called Muller diagram or HS diagram. This is what I extract from internet. I believe it's more informative. Basically, they are the same. There is a phase envelope represented by this heavy line, and there are constant temperature lines, and there are constant pressure lines with the highest slope. So how does, and there are constant quantity lines. So the next thing we're going to ask ourselves, why is this diagram so useful? The reason is because entropy and enthalpy are state functions. Once we are given the fluid, like this diagram is for water, if we are given their temperature and the pressure, we can read their properties from the diagram directory. That is how enthalpy entropy diagram has been used for a long time, for many decades, because it's for engineers, we can just read the numbers from the chart. Now, a few important properties relate to entropy on the TS diagram. If a process involves heat transfer, we can tell from the definition of entropy that it will make a change on the TS diagram. One interesting thing we can say is if the change is toward the right-hand side of the diagram, then dq must be 0. And if it's pointing to the left, then we know dq is smaller than 0. It mainly because if it moves to the left, ds become negative, so dq is 0. So this is understandable. This concept will be used in many cases in the subsequent discussion. And another important property is for a process change the state from state 1 to state 2. On the TS diagram, the area under the curve represent Q. It can also be seen based on the integral of the definition of entropy. The integral of T over ds is the heat transfer term. This is very useful. And we're going to use this slide to demonstrate this interesting property. That is why TS diagram is used very frequently for an adiabatic process. If it's reversible adiabatic combined, we give a term called isentropic process. Remember, this is a very, very important term. If it's a reversible adiabatic, we give a name, and it's called isentropic process. For an isentropic process, because entropy is defined as dq over T, if heat transfer is 0, ds is 0. So every time we see the word isentropic, we have to immediately activate two things in our mind. One is ds equal to 0. The other thing is it means reversible and adiabatic. Okay, these three underlined phrases are actually equivalent. If we see one phrase like isentropic, we have to activate two other concepts immediately. Okay, then if look at the isentropic process, it represents this vertical line because entropy doesn't change. Heat transfer is 0. The area under the vertical line is also 0. So this is a representation of isentropic process. Then if we look at the isosomal process, it's interesting to know as for an isosomal process, temperature remain a constant during the change, and that the heat transfer represent the area under the curve. So the rectangular area under this horizontal line represent the heat transfer of an isosomal process. If we apply what we just saw to the analysis of two Carnot cycles, one is heat engine, the other one corresponds to heat pump. Some interesting results can be revealed from the analysis of the area. Remember, for a heat engine, two segments of the process are adiabatic, two are isosomal. So essentially, we can represent the 4 unit operations associated with a heat engine like these two vertical lines and the 2 horizontal lines. And more than that, QH, if we look at the QH, we say it's going to be the area and this curve, isosomal heat transfer. So TH for the heat transfer from the high temperature reservoir, Q sub H can be easily obtained from the area like this. Similarly, QL can be estimated based on the area and this curve. So that means the lower rectangular area represents QLs. This is a QL. This whole thing is QH. And similarly, for the heat pump, the refrigeration cycle run with 2 isentropic process and the 2 isosomal process. Similar to the analysis of heat engine, the heat being absorbed at a lower temperature represent this area, this rectangular area. Then the heat rejected at a high temperature involve the heat being absorbed at a low temperature plus the work done. So the difference of QL and the QH represent the work. This apply to this heat engine also. If we accept this analysis, we can estimate the efficiency based on what we discussed. The efficiency of a heat pump is this area divided by the total area. The efficiency of a heat engine is this rectangular area divided by the total area. And now let's look at the evaporation process. If On the TS diagram, we know there's a phase envelope, and the evaporation means we have a system involving saturate liquid evaporate to saturated vapor, and it's an isosomal process. So the area under this horizontal line represent the change, heat transfer, and also the enthalpy change. Therefore, for evaporation, we can say the entropy change equal to dq over t, or q over t equal to h over t. Why is q equal to h? That's from the first law. So we have first law embedded in my statement earlier, but the result is very important if we want to estimate the entropy change of evaporation or phase change. It involves the latent heat under the same temperature. So latent heat divided by temperature. Then we are ready to look at the Carnot cycle that involve phase change. This Carnot cycle involves, again, two isentropic process on the TS diagram, two isosomal process. Assume this refrigeration cycle operated in the reversible situations, but the full fluid involve phase change. We are only given two temperatures, only two, high temperature, low temperature. This is like inside the refrigerator, outside the refrigerator, two temperatures. And this from 1 to 2, it represents the compression and the nozzle fluid passing through a nozzle evaporates, partly evaporate, it expands. We are given only two temperatures, but we are also given 2x. State 3 represents saturated liquid. State 1 represents saturated vapor. Then we are asked to find the pressure of state 2. Find the pressure after compression and before the heat rejection. That's this P2, and also determine the COP for the cycle. To begin the analysis, we know state 1 and 3 are on the saturation curves. This is a phase envelope. Therefore, this represents saturated vapor, this represents saturated liquid. So if their temperatures are given, their states are fully given. These two are fully given. Now let's look at the state 2. State 2 is the fluid, represent the fluid from state 1 through an isentropic process. This is an isentropic process. So can we conclude entropy at the state 2 equal to entropy at the state 1? If so, the state 2 is fully given. Do you agree? Because temperature and the entropy are given. Similarly, for state 4, it's a vertical curve down from state 3. So state 3 is fully given. Then state 4, we know the temperature and the entropy. So state 4 is also fully given. That's why I said at the outset, only 2 temperature and the 2 X values need to define the full cyclic process. And we can dig out the entropy for these 4 points from the table. Then this is just like what I said. State 2 state are fully given. Therefore, we should be able to calculate the pressure. Now, the question is how. This is a step I urge you to practice. Very important to practice. Make sure you can do this. You can find P2 from the given temperature and the enthalpy. The way to do it is so we can find 2 numbers, 2 pressures from 2 subtables. From this page, from this table, there are 2 subtables representing 2 different pressures. We can do linear regression. We can get this number. Really, please practice. And after we get this number, we can start answering the second question, determine the efficiency, the coefficient of performance of the cyclic process. It's defined as QH divided by W. Because it's a Carnot cycle, we can simply use the temperatures. Remember, this is what we discussed in the last chapter, and the number is reasonable, 5.55. Now, finally, I'd like to ask you, is it possible to estimate the quality of the fluid at the state 4? I put my answer here, but I urge you to practice to answer this question. You will need to use tabulated result. It's a saturated, two-phase fluid. So you need to dig out the numbers at the 2n and then find out the quality. Okay, let's look at another example. If we have a refrigerant in the piston cylinder device, once we see this, we know it's related to closed system. It's like what we mentioned at the outset. The purpose of this chapter is to introduce you the analysis of entropy change associated with closed systems. Okay, we know the container volume. We are given the fluid initial state fully because it saturates refrigerant at 20 degrees C. If the piston expands reversibly at a constant temperature and it expands to a pressure 400 kilopascal, we are asked to find the work and the heat transfer associated with this expansion process. So the way to tackle this problem is, we know this is an expansion process. The way I analyze this problem is through, I first ask myself, what is the phase of the ending state? Is this going to be a two-phase or single-phased fluid? We know isosomal expansion follow a horizontal route on the PV diagram. It expands, so it can remain as a two-phase, but it may also expand further to superheated region. So how do we judge if it's two-phase or one-phase? We look at the saturation pressure at this temperature, because the isosomal process look like this. On the PV diagram, isosomal process look like this. So we look at the saturation pressure of this refrigerant at this temperature, given temperature. Is this going to be higher or lower than the ending pressure? And what I found is the saturation pressure is pretty high. So that means the given pressure is lower. That also means the fluid expands further into the superheated region. Okay, with this in mind, the problem becomes easier. So we know the temperature and the pressure of the ending state also. So we can begin the analysis. The full analysis includes both energy balance and the entropy balance, and entropy equation. So both first law and the second law are activated. First law says for a closed system, the internal energy change between the two states equal to Q minus W. And the entropy change based on the definition equal to dQ over T. Then in order to answer both Q and the W, the question about Q and the W, we have two equations. So we are ready actually to answer the question about Q and the W, because this integral can be simplified simply to Q over T. It's an isosomal process. Then we have two equations, two unknowns. From the first thing we look at are the property data are going to be available in the tables. Internal energy and the entropies are all available in the table in the textbook. So we can use the tabulated value to estimate internal energy change and the entropy change. We know we also need to calculate the total mass. Total mass can be estimated because we are given the volume of the container. We know the initial temperature and the pressure. So once the mass is given, is known, we can calculate the heat transfer and the work done based on the first law and the second law. This concludes the discussion of entropy and its relation with reversibility and how it can be applied to the analysis of heat engine and the heat pump. This concludes my first part of chapter 6.